myself. I'm a Kotlin GD. I've been working as a software engineer for over 30 years now. I've been working in the Android iOS ecosystems since 2008, or 2009 even, I think. So as the title suggests, we're going to talk today about a couple of key areas that I feel are contributing to the increasing convergence of native iOS and Android development. An emphasis on native here, by the way. First up, we'll cover some examples how similar the Kotlin and Swift languages are. This isn't necessarily something new, but is, of course, an important element to this dynamic. But as useful as that is, what I think is more impactful is the very similar approaches we now have on iOS and Android for both UI development, using Jetpack Compose and Swift UI, and more recently, the fact that we have much the same mechanisms available for managing concurrency in both platforms. Just also mention somewhat in the context of both platforms using declarative UI frameworks is I think that we've converged to a large degree on the use of MVVM, or typically unidirectional data flow type variations of it. Lastly, not something I'm going to talk about in any detail, but interesting to note, I think, how similar Android and iOS devices have become and the closer alignment of UX patterns. So the usual quick poll, I'm assuming mostly Android developers here, but just curious, anyone here doing iOS development? Okay, quite a few, wow. And how many of you are using Swift UI? Good, most people probably. And lastly, how many people are using new Swift 5.5 concurrency functionality? Okay, slightly smaller number. It's funny, I gave a version of this talk at Swift Heroes in Turin a few months ago with, of course, the questions reversed, and I got one brave soul hiding away in the corner admitting he was an Android developer. Okay, so just wanted to show at this point some of the key milestones that have brought us to where we are today. Both platforms started growing in earnest around 2008, 2009. And of course, at that point, we were developing apps using Java on Android and Objective-C on iOS. And these, by the way, were some of the devices that we had at the time. The tiny, by today's standards, iPhone 3G, and the Android G1 with this funky pull-out keyboard. Needless to say, devices on both platforms have changed a lot since then, and as mentioned, have become significantly more aligned. Fast forward to 2014, Swift is now supported on iOS, and 3 years later, Kotlin on Android. Languages, as we've mentioned, that are significantly more similar to each other than Java is to Objective-C. 2019 then was a key year for UI development on both platforms. Jetpack Compose was announced at Google I/O that year and formally released in 2021. Swift UI then was announced at WWDC and released later that year. And lastly, we saw the announcement of the new Swift 5.5 concurrency functionality at WWDC 21. Just some brief additional background and context before I dive into the comparisons. This was an article written in April 2019 by Jesse Wilson, talking even at that point about how Android and iOS development was converging. He was primarily basing this on similarities in the language, device UX alignment, and actually mobile team organization as well. But within 2 months of that article, we see announcements of frameworks on both platforms would have a much bigger impact on that convergence. First off, a few weeks later, we saw the announcement of Jetpack Compose at Google I/O. And then about a month after that, Swift UI was announced at WWDC. And in terms of my own interest in this area, I had at that time, as part of the Kotlin multi-platform work I was doing, been developing a native iOS application. And as someone that hadn't really been opening up Xcode that frequently for a while, I always struggled to remember again how to set up storyboards and view controllers and table views. I'd seen the announcement of Jetpack Compose at Google I/O, but to be honest, a little abstract for me at that stage. I didn't really appreciate what declarative UI was all about or the impact it would have on mobile development. I was watching WWDC then. I saw the announcement of Swift UI. It was available in Xcode beta that evening, and in the early hours of the morning, I had my first basic Swift UI app. And I finally appreciated what declarative UI offered and how intuitive it made UI development. Something down the road, I think that would be many people's experience using Compose on Android for the first time. By the way, one interesting point worth noting here as well, I think, is the different sequence in which some of these capabilities became available on each platform. On iOS, we started with declarative UI and then later added structured concurrency, whereas it was the other way around for Android. I think this has some implications for how existing functionality has evolved on both platforms. Okay, let's dive into some of the comparisons. Firstly, the languages themselves. So I'm not going to do an exhaustive comparison of Kotlin and Swift. Rather, I'm going to use a number of examples to illustrate how they compare. So John Sundell wrote this article recently on different ways of iterating over Swift collections, and I thought it would be interesting to see what the Kotlin equivalent would be. So if we look at the first few examples from the article, probably won't take people too long, but at a glance, can folks spot which is Swift and which is Kotlin? Yes, yes. And if we add in the array declaration, it's a little clearer which is which. Difference as mentioned, the use of parentheses, let versus val, print versus println, for example, but clearly very similar other than that. A few more from that article, and again, a key thing here is how, at a minimum, Swift is at least very readable to someone who knows Kotlin and vice versa, and probably wouldn't take a developer from either platform that long to figure out how to write the code for the other. And lastly, from John's article, we see some examples of iterating over maps, and I think we see even closer similarities here, map variable declaration aside. Okay, lastly in this section, another recent article, this time for Saroon, talking about sorting Swift arrays. And again, we see the similarities. APIs almost identical in initial examples, and then some differences in how we set up custom comparators, for example. But easy to understand either approach. And by the way, we'll see some additional comparisons of the language in the next few sections where we talk about structured concurrency and declarative UI. So we're getting to what I think are the more impactful similarities we have today. Firstly, the use now of declarative UI frameworks on both platforms, Swift UI on iOS and Compose on Android. Most folks here are probably somewhat familiar with Compose, but just to level set somewhat. So a common way of explaining declarative UI is in terms of the what versus the how. With declarative UI, we declare what our UI should look like in a particular state, and state is very important in this context. Any changes in state cause the appropriate parts of our UI to be re-rendered or recomposed. Another interesting implication of this approach then is that it at least encourages use of MVVM on both platforms. Typically, as mentioned, unidirectional data flow type variations of it. As well as SwiftUI and Compose, it's also the approach used in the likes of React and Flutter. And as we mentioned earlier, SwiftUI was released in 2019 and Compose in 2021. So I'm going to illustrate again with a few examples. So this was a tweet from Thomas Rickward about a GraphQL SwiftUI sample he created using the Apollo library. I'd been using Apollo in shared Kotlin multi-platform code, so I thought it would be interesting, with Thomas's blessing, to create a Compose and SwiftUI version of that project that consumed that shared code. These are iOS and Android screenshots from the sample, and we're going to drill down and compare, for example, how a row in this list would be represented in SwiftUI and Compose. So at a glance, we firstly see that SwiftUI uses structs to represent UI elements like this, whereas Compose uses Kotlin functions. But if we ignore what you might call the outer wrapping around the UI elements, I think we see more closely how similar these are. Some differences, of course, like HStack, VStack in SwiftUI versus row column in Compose. We have async image in both SwiftUI and Compose to display an image from URL. There's text elements in both, with some differences then in how styles, etc., are applied. But again, the key thing is here how closely the concepts align, how easy it's becoming for a developer to sort of translate the UI from one platform to the other. And hearing more and more stories where this is happening. UI might be originally done in SwiftUI, and then a Compose version is done based on that, or vice versa. Another example from one of the samples I have, this time illustrating use of Canvas in both SwiftUI and Compose. This particular sample makes use of what's called a chip-aid emulator in shared Kotlin multi-platform code. This was an instruction set used in the arcade games of the past, like the ones, for example, out in the common area. The emulator code generates an array of display data as it runs this program, and we want to show that then in our app UI. And we're able to, as I said, to use Canvas in both SwiftUI and Compose, with, again, very similar code used in both cases. Here, we're iterating over that virtual display data we're getting from the emulator as it runs this program, and then using Canvas APIs on both platforms to update the UI. Again, small differences in the APIs used, but again, fundamentally the same approach. And one more example from another sample I have, this time for this Fantasy Premier League app, using SwiftUI and Compose. I'm not sure if there's any Liverpool fans here, but you may notice this was taken at a time when they're having a little bit more success. Again, we see the similarities in structure here, and in particular, if we focus in on the UI elements. Some differences, again, the APIs used and how styles and padding, etc., are managed, but much the same other than that. And in general, if we think of our UI as a tree of components, what we typically see is closer similarities for ones like this, but with some perhaps bigger differences then we get to screen-level representation in terms of, for example, how navigation is managed, but still conceptually the same approach being used. But speaking of navigation, there were some SwiftUI changes announced this year that make the approaches to navigation and a number of other areas actually even more aligned than before. First up, navigation. This is a pared-down example from Compose code in the people in space sample, showing some of the key moving parts of how navigation could be managed using navhost and composable then for each destination. And this is what this might look like in SwiftUI now with iOS 16 updates, using navigation stack and navigation destination, which maps somewhat loosely to compose as nav host and composable. Some difference still in that compose uses route-based approach, whereas SwiftUI maps to destinations using the data type, for example, the assignment class here. Different handling of start default destination, but at least these updates, I think the approaches are certainly more closely aligned than before. Next iOS 16 updates is the addition of chart support in SwiftUI. This is an example of it here on the left, along then an example in Compose using third-party library called Qualiplot. I'm also showing this here as a nice segue, I think, to an interesting point about the SwiftUI Compose ecosystems. Swift Charts is provided directly by Apple. And there's an expectation in general that Apple will provide most of the libraries a developer will need when developing iOS apps. Whereas, of course, on Android, there's more of a tradition that many of the solutions will come from third-party offerings like this. Next up, any layout, also added in iOS 16, explained as, for example, something that enables dynamically changing the type of layout container without destroying the state of its subviews. It's quite a mouthful. But similar then to a relatively recent addition to Compose, which is movable content of. Again, similar example from the documentation, where it talks about how you can use to produce a composable that moves its content between a row and a column based on a parameter. So different syntax, but quite similar and very useful capability now on both platforms. Another small change with iOS 16, text fields that automatically grow with their content, and again brings in line with Compose behavior. And interesting to note here is the same use of text field in both SwiftUI and Compose. Next up, example of showing partially visible bottom sheet in SwiftUI, again added in iOS 16, and again providing capability that's also available in Compose. And yet another of these SwiftUI announcements from this year, this one in relation to applying text styles across a group of controls. Relatively small change, but again, one that shows, as I keep saying, that sort of closer alignment. In this example, we're applying bold text style to all elements within the VStack in SwiftUI and column in Compose. Using provide text style then in Compose to achieve the same purpose as that font weight view modifier in SwiftUI. Semantics a little different, but again, same concept being applied in both cases. One last example showing swipe to refresh functionality in SwiftUI and Compose, with latter in this case provided by the Compose accompanist library. Just to also point out is in the previous text style example, the slightly different approach for applying behaviors like this. SwiftUI uses what are called view modifiers, example refreshable here, whereas Compose tends to sort of wrap code to apply behavior, or sometimes uses sort of the modifier type approach. But once you see that sort of difference in approach, tends to sort of make the translation that much clearer as well in that case. Interesting to note that we can now use declarative UI frameworks for watch devices on both Android and iOS. The Compose for Wear example on the left was contributed to the People in Space sample. And on the right, we see WatchOS version based on use of SwiftUI also contributed to the same project. And again, similarities in the approach being used. Lastly, in this section, thought it was interesting that not only do we now have support for widgets on both platforms, but again, the same declarative UI approach for developing them. Next up, concurrency. And more specifically, we're talking about the structured concurrency functionality we now have on both platforms. This is a really powerful capability that allows us to write async code in a way that's easy to read and also allows a more deterministic structured approach to error handling and cancellation, for example. A key enabler of this is the ability to have code that can be suspended and resumed at a later point. And as we'll see in a moment, Swift supports these through capabilities like tasks, async functions, async sequence, and Kotlin similarly through coroutines, suspend functions, and flow. This approach, for example, allows executing async functions both sequentially and in parallel, and we're going to show examples of both shortly, along with some examples of use of async sequence and flow. And a very important aspect of this is how invocation of code like this can be tied into the UI lifecycle, thus allowing, for example, automatic cancellation when the UI is no longer shown. Just to also mention at this point that the new Swift concurrency capabilities we're talking about here were included in Swift 5.5 that were announced at WWDC last year. So firstly, let's look at an example of executing async functions sequentially using slightly adapted version from Paul Hudson's excellent series on Swift concurrency. Here we have 3 Swift async functions: fetch weather history, calculate average temp, and process weather, which itself is an async function. Some of these would, for example, make a remote API request and have to wait for the response. And this is the Kotlin equivalent. We see here the use of suspend keyword in Kotlin versus async in Swift. Again, both denoting a function in which suspension can occur. And also the fact that we explicitly use await in Swift, where suspend functions can be called directly in the appropriate context in Kotlin. Looking then at some examples, small examples of how we can invoke async code like this, again using Paul's examples as a basis. It can be invoked from a main function shown here, marked again as async in Swift and suspend in Kotlin. We can also create a specific task in Swift, and similarly in Kotlin create a coroutine from which it can be invoked. What I think is interesting then, I think, is how we can tie this into our UI lifecycle, like along importantly then with automatic cancellation when the UI is no longer shown. We use the task view modifier in Swift UI for this and can use, for example, launch defect in compose. And we'll see another example of this later. Also interesting to note that we can change behavior on both platforms here such that the code will be invoked when a particular key changes. Whereas the previous example showed how we can invoke async functions sequentially, Donnie's article about use of Swift's async let, an associated example, shows how to invoke tasks concurrently. And this is again a slightly modified version of the sample and shows how we can kick off a number of tasks and let them run in parallel and wait for them to complete. And we'll see this in a bit more detail in the next slides. And again, this is the Kotlin equivalent. And if we break it down a bit more, we see again the use of async in Swift and suspend in Kotlin. Very similar mechanisms then for invoking these async functions in parallel, using async let in Swift and async coroutine builder in Kotlin. And then waiting for them to complete using await in Swift and await all in Kotlin. In this case here, we're going to load a list of movies and user info and wait for them to finish. And these requests, as I mentioned, will execute in parallel. Finally, we kick off a number of other async tasks that will again execute in parallel and again wait for them to complete. The other major component of new Swift concurrency functionality is async sequence, and that allows asynchronous iteration over stream of values. And this is something that maps very closely to a Kotlin flow. Shown here are some basic examples adapted again from Paul Hudson's articles of use of async sequence in Swift, and I've added then similar examples of use of flow in Kotlin. Again, we use for await in Swift to iterate over the values, and we use collect in Kotlin. And then also a few examples of some of the operators supported. Firstly, using map to convert each value to its uppercase version. And again, iterating over the result. And then filter, for example, to filter on a particular string, again in a very similar manner. So as I was preparing this section of the talk, and in particular looking at ways in which Swift async sequence operators compared to those supported by Flow, I read a few articles like this talking about aspects of the Swift combine framework that were still missing from async sequence at the time. There was still a gap that meant in some cases people still needed to rely on combine or third-party libraries like async extensions here that mimic some of the functionality provided. So I was, of course, interested to see the Swift async algorithms package announced. And with this, we now effectively have even closer mapping between the operators supported by Swift async sequence and Kotlin Flow. And this is a few examples using some of the new operators included in that async algorithms package, along with their Kotlin equivalent. Using new async method provided by that package to convert a Swift array to an async sequence, with asFlow being used in Kotlin to achieve the same purpose. And as before, we use for await in Swift and collect in Kotlin, showing an example firstly of merge, and then zip here, and several other operators in common now as well. Just to finish off the section, I want to show one other example of how we're now talking about very similar concepts on both platforms, using in many cases the same vocabulary. I'd watched a session at bottom right at Kotlin Conf in 2019 where Florina and Manuel talked about cancellation of coroutines and how they needed to be cooperative. I thought it was interesting then to see the structured concurrency talk at WWDC 21, talking about the same concepts, talking about cooperative cancellation of tasks in the Swift case. I'm going to talk just very briefly about Kotlin multi-platform, as it's something that I think nicely complements some of the developments we'll be discussing here, again in the context of developing native applications and in relation to sharing non-UI code. Subtitle here, obviously not the official one, but phrasing like this to perhaps emphasize where this potentially fits in. And bring Kotlin multi-platform up here as well, as we'll see a small example of a little while of how some of the similarities we're discussing here make the consumption of shared Kotlin code, including async code related, pretty seamless in Swift. And a key component in Kotlin multi-platform that's of interest to us here is Kotlin native. It provides capability to compile Kotlin code natively using, for example, LLVM on iOS. Typically, a framework is created from which can be consumed directly in Xcode. And very importantly, we can access native APIs directly from the shared code if needed. And last point here is something I'll be doing in a few samples, which is nice capability now to build shared code as a Swift package and add that to an Xcode project like any other library. Just showing here how Kotlin and Swift types are mapped to each other when using Kotlin multi-platform. I'm not going to go through these, but just to give a flavor, and we'll see some of these in a number of the examples in the next talk. But also using this as a segue to mention a number of other developments. For example, the use of KSP and Kotlin compiler plugins for generating code. This provides a sort of an approach to generate sort of more richer mappings interop between Kotlin and Swift using KMP. Thaddeus, you might have seen Thaddeus and Pamela's talk earlier on KMP. Thaddeus also gave a talk at droidcon New York about Kotlin compiler, and this is an approach that we're seeing increasingly being used. And talking about another library in a little while that uses that same approach. But as I said, it's something TouchLab as well have been talking about developing some capabilities that, again, to sort of address some of the disconnect that people who work on Kotlin multi-platform are probably aware of in terms of some of the Swift and Kotlin concepts that don't directly align with each other. So we're going to finish up with a few examples that illustrate again some of the areas we've been discussing. So this is based on another sample I have in GitHub called Bike Share. This sample includes broader functionality, but for illustration purposes here, we're going to focus in on showing a list of what are called bike stations for a particular bike network, in this case one for a bike sharing network here in London. This is what the high-level architecture might look like for an application like this. We're building native iOS and Android apps using Xcode for iOS and Android Studio for Android, using SwiftUI on iOS and Compose on Android and MVVM on both. We then, for example, have a shared Kotlin repository that we're consuming on both platforms. And this is an excerpt from that shared repository that we're going to use in the example. It pulls for info for a particular bike network and exposes that as a Kotlin flow, something we'll use directly in our Android client, but will be mapped to an async sequence in our iOS client. And by the way, we're mapping from that flow to an async sequence using the really nice KMP native coroutines library that I'd strongly recommend anyone working on Kotlin multi-platform to take a look at. It supports new Swift 5.5 concurrency capabilities along with a number of other frameworks. So firstly, this is what a view model might look like in this example. Typically, its purpose is as a container of observable state, changes to which will then cause UI to be re-rendered. This is sort of a conduit for actions we're taking from the UI that would typically cause that state to be updated. Also can be used for transforming state we get from other parts of the code to something more suitable for the UI, though not using that in this basic example. The pattern here for iOS is pretty common, using observable object protocol along with publish property wrapper. On Android, we're using AAC view model and also using Compose's mutable state of here to represent the observable state we're exposing from the view model. Not too important in this context, but common also to use something like stateflow here as well as mapped to a specific UI state as mentioned. And on iOS, we have a poll network updates async functions, which uses the new for-await mechanism in Swift, along with use of that KMP native coroutines library that I mentioned, that maps the Kotlin flow shown in the previous slide into an async sequence. On Android, we're doing something quite similar, in this case, consuming the flow directly, and again, using Kotlin flow collect instead of the for-await we use in Swift. On both platforms, we're also triggering, when we get new data, update of some state that would cause SwiftUI and Compose to re-render the appropriate parts of the UI. And this is what some of the SwiftUI and Compose code looks like in this example. Again, we're using Swift struct for SwiftUI and a Kotlin function for Compose, using list in one and lazy column in the other to iterate over the list of stations coming from our view model in both cases. We use the task view modifier in SwiftUI to invoke the poll network updates async function in our iOS view model, and use launched effect in Compose to do the same thing on Android. And important to note again that these will automatically get cancelled when our view disappears. And by the way, that cancellation will also get propagated to the flow in the shared code in both cases. Before we show the SwiftUI and Compose code for the rows themselves, just recap on what we're trying to show here. We have a row with a tinted image representing how many bikes are available, and then a column containing the name of the station and availability info. And this is what the SwiftUI looks like for now. A lot to unpack here, and we'll show Compose equivalent next and show a trimmed down version of both side by side to illustrate the comparisons. But here we can hopefully see general structure with image showing the tinted icon, color based on number of bikes, and then a SwiftUI HTAG text elements, etc. And by the way, this is from a sample in GitHub if people want to look through this in more detail. And this is the Compose equivalent. Don't worry again about the details too much, but much the same structure as the SwiftUI version. And we'll see clear comparison in the next slide. And then this is the pared down version shown side by side. Again, hopefully we can see how the UI elements map very closely to each other. HStack to flow, VStack to column, image, spacer, and text elements with some API differences, and as mentioned before, and how styles and padding, etc. are applied. So in the previous slide, I took out the tinting code just to allow clearer comparison, but just showing it here as well explicitly, and again, something that can be done quite similar in both platforms. Okay, next example illustrates use of combining multiple Swift async sequences in an iOS app, one of which is in fact mapped to a Kotlin flow. First one representing a list of players. This one is mentioned mapped to a Kotlin flow using that KMPK native coroutines library mentioned earlier. The other then representing a search query, and then using combine latest operator to combine them. And I think this nicely illustrates, again, how seamless that consumption of a Kotlin flow in Swift can be. One last example, similar to the last one, this time from a confetti sample that displays conference information. We can see here, firstly, the Android view model, where we use combine to create a mutable UI state based on flows coming from a repository and shared KMM code. Very common pattern in a sort of modern Android application. And then very similar code in the iOS view model using Swift async sequence combine latest, where we used combine on Android. And some of the async sequences we're combining are again mapped under the hood to the same flows that from the shared repository. So that was somewhat of a whirlwind tour of some of the areas that I think are contributing to the increasing convergence of native iOS and Android development. And just to recap, there are, of course, many different permutations in terms of how mobile teams are organized, in terms of the company, based on the company, the size of the project, etc. But we at least now, I think, have more possibilities for people working on both platforms and becoming more general mobile developers. We've seen similarities in language, but even more important and impactful are the common approaches we now have for both UI development and concurrency on iOS and Android. And complementing that, I think, is the possibility of using Kotlin multi-platform for sharing parts of the boring non-UI code on both platforms. Thank you.